And now in this lecture we'll answer on two questions. In the first question, we'll find out the area of this circle that is inscribed by this trapezoid ABCD. And in the second question, we'll find out the length of this line segment QB that is equal to x. So we'll start with the first question. In the drawing, we have trapezoid ABCD that blocks this circle. In addition, we know that this is line segment AM that is equal to A units in its length. This is line segment MB that is equal to B units in its length. Again, our mission is to find out the area of this circle that is inscribed by this trapezoid ABCD. So first of all, we define the center of this circle. This point is point O. And we define the point of tendency of tangent AD with this circle. This point is point P. And we define the point of tendency of this tangent BC with this circle. This point is point Q. Here we can implement rule 2. I'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing we have a circle, and this is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB, and according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can implement rule 2 in our drawing. One, because in our drawing, if we focus on this common external point, point A, from this common external point, point A, we have two tangents to this circle, tangent AP and tangent AM. And according to rule 2, they are equal to each other. That is to say, AM equals to AP. But AM equals to A. Therefore, AP must be also equal to A. Because they are equal to each other according to rule 2. So AP equals to A units in its length. Write it down. Likewise, we focus on this common external point, point B. From this common external point, point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM equals to B units in its length, according to what is given in the question. Therefore, tangent BQ must be also equal to B because they are equal to each other according to rule 2. So, tangent BQ equals to B units in its length. This is tangent BQ that is equal to B units in its length according to rule 2. The next step, we join, again, point O is the center of the circle, so we join points O and Q together by a straight line. Point O is the center of the circle, point Q is the point of the circle itself, so this is exactly the definition of a radius. Therefore, OQ is the radius of this circle. We define the radius of this circle as x. So OQ equals to x. This is the radius of this circle according to our definition. And because of the fact that the radius OQ that is equals to x, the radius OQ is drawn to point Q, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and P together by a straight line. OP is of course the radius of this circle that is equal to x, and because of the fact that the radius OP that is equal to x, the radius OP is drawn to point P, that is the point of tendency of tangent AD with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, And this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we will do a construction. That is to say, from this point, point A, we will go perpendicular on BC. Again, from this point A, we will go perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point N. By doing this construction, we created those two angles. Those two angles are both defined as one-sided interior angles. We also know that ABCD is a trapezoid, and the definition of a trapezoid is a quadrilateral with one pair of parallel sides. So in this trapezoid ABCD, side AD is parallel to side BC. So by doing this construction, we created those two one-sided interior angles, and those two one-sided interior angles are located between the parallel lines AD and BC. And therefore, according to Rule 17, and the sum of those two one-sided interior angles is equal to 180 degrees. So repeat clicking on Rule 17. The sum of one-sided interior angles that are located between two parallel lines is equal to 180 degrees. So in the drawing we have line A that is parallel to line B. This is the red line C that intersects with those two parallel lines A and B at those 2 points. In addition, we have those two angles alpha and beta that are defined as one-sided interior angles. And because of the fact that those two angles alpha and beta that are one-sided interior angles are located between the two parallel lines A and B, the sum of those two angles must be equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. So we should implemented Rule 17 in our drawing. We already implemented because, as I mentioned before, the sum of those two angles must be equal to 180 degrees because of the fact that those two angles are defined as one-sided interior angles and they are located between the parallel lines AD and BC. And according to Rule 17, the sum of those two angles that are located, the sum of two parallel, the sum of one-sided interior angles that are located between two parallel sides must be equal to 180 degrees. Therefore, the sum of those two angles must be equal to 180 degrees. But this angle equals to 90 degrees, according to our construction. So 90 degrees plus the size of this missing angle in total must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do another construction, that is to say from point O, this point O that is the center of this circle, we will go perpendicular on AN. Again, from point O, we will go perpendicular on AN. So actually, this angle equals to 90 degrees, and this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AN, this point is point T. By doing this construction, we will have the small quadrilateral APOT. Inside this small quadrilateral APOT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Likewise, in the lower quadrilateral TOQN, inside this quadrilateral TOQN, we have 3 right angles. 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4th missing angle in total must be equal to 360 degrees. Therefore, this 4th missing angle must be equal to 90 degrees in its size. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So actually found out that the big angle POQ is equal to 90 degrees plus 90 degrees, that is 180 degrees. So the big angle POQ is equal to 180 degrees in its size. And we know that any angle that is equal to 180 degrees, it is a straight line. Therefore, POQ, line segment POQ is a straight line. Line segment POQ is a straight line. If line segment POQ is a straight line, then PQ is also a straight line. So PQ is also a straight line. Or line segment PQ is a straight line. So actually, in shape APQN, in this shape APQN, we have 1, 2, 3, 4 sides. So write it down. In shape APQN, we have 4 sides. And therefore, shape APQN is a quadrilateral. Shape APQN is a quadrilateral. But in this quadrilateral APQN, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral APQN as a rectangle because it has 4 right angles. So I write it down. Quadrilateral APQN is a rectangle according to rule 5 because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle APQN, side AP must be equal to the opposite side QN. But APZ, therefore QN, the opposite side QN, must be also equal to A units in its length. Likewise, according to the same rule, in the same rectangle APQN, side PQ must be equal to the opposite side AN, but PQ in total is x plus x, that is 2x, therefore AN must be also equal to 2x units in its length. AN equals to 2x units. What is the length of the missing line segment? Line segment BN. The length of BN, it is very easy to see from the drawing that BN equals to BQ minus NQ. Again, BN equals to BQ minus NQ. So I write it down. Bn equals to bq minus nq. So Bn in total equals to bq is b, minus nq is a. So in total Bn equals to b minus a units in its length. So Bn equals to b minus a. The length of side AB is a plus b. Again, the length of this side AB is a plus b. The next step, and copy the right triangle A and B in a new page, and implement the Pythagoras theorem on this right triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse AB equals to a plus b units in its length. Side Bn equals to b minus a units in its length. And side An equals to 2x units in its length. Here, by Pt is the evaluation for Pythagoras theorem. So actually, this is the right triangle ABN that is going from the original drawing. In this right triangle ABN, according to the Pythagoras theorem, AB square equals to AN square plus BN square. So I write it down. So AB squared, that is the square of the hypotenuse, is equal to AN squared plus BN squared. AB is A plus B, therefore AB squared is A plus B squared, and it is equal to AN squared. AN is 2x, therefore AN squared is 2 squared, that is 4 times x squared. So in total AN squared, in total 2x squared is 4x squared. Plus Bn squared. Bn is B minus A, therefore Bn is B minus A squared. So according to the Pythagoras theorem, in this right triangle ABN, we shall find out that A plus B squared equals to 4x squared plus B minus A squared. We open the brackets on both sides of this equation, and we get that A plus B squared equals to A squared plus B squared plus 2 times A times B, and it is equal to 4x squared plus B minus A squared. B minus A squared equals to B squared plus A squared minus 2 times A times B. So here we have A squared on both sides of this equation, so A squared will get cancelled. And we have also B squared on both sides of this equation, so B squared also gets cancelled. So we cancel those two expressions, and this side of the equation we left only with 2AB. And in the other side of the equation we left with 4x squared minus 2AB. Okay, we found out that two AB equals to 4x squared minus 2AB. Here we let 2AB to this equation, and we get that two AB plus 2AB is 4AB, so 4AB equals to 4x squared. Here we divide this equation by 4, and finally get that 4AB over 4 is AB, equals to 4x squared over 4 is x squared. So in total, we found out that x squared equals to AB. Our mission is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. And again, the area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of this circle must be equal to pi times the radius of this circle squared. So it is pi times the radius of this circle squared. The radius of this circle is x, therefore the radius squared is x squared. So in total, we found out that the area of the circle is equal to pi x squared. What we just right now found out that x squared equals to AB. Therefore, we substitute x squared in this equation by AB, and we get that the area of the circle is equal to pi times x squared, and x squared is AB. So in total, we found out that the area of the circle is equal to pi times AB square units. And that is the answer to the question. I repeat again. We actually found out that the area that we are looking for in this question, that is the area of this circle, is equal to pi times AB square units. So we finish with the first question. In the next step, I will present to you the second question, and we solve the second question of this lecture. In this second question, our mission is to find out the length of this 9 cm cubed that is equal to x. So we have to find out the value of x. So in the drawing we have a semicircle. This is a semicircle. Inside this semicircle, this is called a P that is equal to 10 units in its length. This is all called PQ that is also equal to 10 units in its length. AB is the diameter of this semicircle, so we know that the diameter of this semicircle, AB, equals to 30 units in its length. And QB is the missing side, so we have to find out the length of chord QB is equal to x. So we have to find out the value of x. So first of all, we define the center of this semicircle. This point is point O. And we know that the diameter of this semicircle is equal to 30 units in its length. If the diameter is 30, then the radius must be equal to half of it. So the radius of this circle is 30 over 2, that is 15. Point O is the center of this semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle that is equal to 15 units in its length. Likewise, line segment OB is also the radius of this circle that is equal to 15 units in its length. In the next step, we join points O and P together by a straight line. OP is of course the radius of this semicircle that is equal to 15 units in its length. In the next step, we'll complete the semicircle to a circle. And we'll extend the radius PO by a straight line until it touches the circle. This is the touching point of the extended radius PO with this circle. So we define the touching point of the extended radius PO with this circle. This point is point M. In the next step, we join points M and B together by a straight line. Angle MOB and angle AOP, those two angles, they are both defined as vertex angles, and we know that vertex angles are equal to each other. So if you define this vertex angles AOP as theta, then this vertex angle MOB must be also equal to theta because they are equal to each other. In the next step, we'll prove that this triangle AOP can go into this triangle MOB. Okay? So we have to prove that this is triangle AOP. This is going to this triangle OMB. So why those two triangles can go into each other? First of all, side OP of this triangle AOP is equal to side OM. OM is also the radius of this circle that is equal to 15. It starts from the center, that is point O, and ends at point M, that is the point of the circle itself. This is exactly the definition of a radius. Therefore, OM is the radius of this circle, that is 15. So side PO of the triangle AOP is equal to side OM of triangle OMB. The above the radii of the circle is equal to 15, therefore they are equal to each other. Repeating again, we shall find out that side PO of triangle AOP is equal to side OM of triangle OMB, above equal to 15. That is the radius of the circle, therefore they are equal to each other. In addition, those two vertex angles are equal to each other. So this is angle AOP in triangle AOP, and it is equal to this angle. This is actually angle MOB in triangle OMB. So angle AOP equals to angle MOB. According to the rule that vertex angles are equal to each other. And finally, side AO of triangle AOP is equal to side OB of triangle OMB. They are both the radii of the circle, that is equal to 15 units, therefore they are equal to each other. AO equals to OB. They are both the radii of the circle, is equal to 15, therefore are equal to each other. So we actually proved that a triangle AOP can go into a triangle OMB according to side angle side rule. We have those two sides and the angle that included between those two sides in triangle AOP are correspondingly equal to those two sides and the angle that included between those two sides in triangle MOB. Therefore, those two triangles can go into each other according to side angle side rule. So I'll write it down. If we found out that triangle AOP congruent, this is the sign of congruent to triangle OMB according to side angle side rule. And from the fact that those two triangles can go into each other, we will derive that the following relationship exists between them. We will derive that side AP of triangle AOP is equal to side MB of triangle OMB. AP equals to MB. AP equals to MB according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AP and MB, must be also equal to each other. But AP equals to 10 units in its length according to what is given as the question. So we can write here that AP equals to 10, and from this equation 10 equals to AP equals to MB, we will derive that MB also equals to 10 units in its length. This is side MB that equals to 10 units in its length. Chord PM passes through point O, that is the center of this circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. So PM is the diameter of the circle and also the diameter of the semicircle. So I'll copy this semicircle with the diameter PM. Again, I will copy this semicircle with the diameter PM and analyze this semicircle. Okay. So here, this is the semicircle with the diameter PM that are coming from the original domain. PQ equals to MQ, PQ equals to MB, this is letter B, so PQ equals to MB equals to 10 units in its length. So in the next step, we'll extend chord MB and chord PQ until they intersect with each other. So here, this is their touching point. And we find their touching point, this point is point E. Actually, we extended the two line segments PQ and MB. They are equal to each other in their lengths. When you extend two line segments that are equal to each other in their lengths until they intersect with each other, then EB must be also equal to EQ. Okay, because of the fact that MB equals to PQ. When we extend those two line segments that are equal to each other in their lengths, then BE must be also equal to QE. So if we define the length of QE as Y, then the length of EB must be also equal to Y because they are equal to each other. So in total, the length of side EM is Y plus 10, and the length of this side EP is also Y plus 10. So from this equation, we derive that EM, so from those two equations, we derive that EP equals to EM. EP equals to EM. That is to say, we should find out that in triangle EPM, this is triangle EPM, side EP equals to side EM. Therefore, it is an isosceles triangle. And we know that in front of equal sides in the triangle, there are equal angles. In front of this side EP, we have this angle, that is angle PME, and in front of this side EM, we have this angle, that is angle MPE. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. So we have here, this is quadrilateral PQBM. Inside this quadrilateral quadrilateral PQBM is inscribed by this semicircle. If we complete this semicircle to a circle, then quadrilateral PQBM will be inscribed by a circle. Okay. Actually completed the semicircle to a circle, and we can see from the drawing that this is quadrilateral PQBM that is described by this circle. And we have the rule that says that if a quadrilateral is inscribed by a circle, then the sum of its two opposite angles is equal to 180 degrees. So I put click on the rule. According to the rule states that if a quadrilateral is inscribed by a circle, then the sum of its two opposite angles, is equal to 180 degrees. I repeat again. According to the new rule, if a quadrilateral is inscribed by a circle, then the sum of its two opposite angles is equal to 180 degrees. So in the drawing we have a circle. This is quadrilateral ABCD that is inscribed by this circle. And according to this rule, because of the fact that this is quadrilateral ABCD that is inscribed by this circle, the sum of its two opposite angles must be equal to 180 degrees. Those are the two opposite angles of quadrilateral ABCD, and therefore according to this rule, the sum of those two angles must be equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees according to this rule. Likewise, those are the other two opposite angles, and according to this rule, angle 1 plus angle 2 must be also equal to 180 degrees in their size. Okay, so can implement the new rule in our drawing, because in our drawing we have this is quadrilateral MPQB that is described by this circle, and according to the new rule, the sum of which two opposite angles must be equal to 180 degrees. This is angle beta, so angle beta plus this missing angle, in total the sum of those two angles must be equal to 180 degrees. Therefore, this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the opposite angles of a quadrilateral that is described by a circle. Likewise, those are the other two opposite angles. The sum of those two opposite angles must be equal to 180 degrees. But this is angle beta, so angle beta plus this missing angle, in total the sum of those two angles must be equal to 180 degrees. Therefore, this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. It is the sum of the opposite angles. This quadrilateral PQMP that is described by a circle. So in total we found out that this is angle beta and this is angle 180 degrees minus beta. The sum of those two angles is 180 degrees minus beta plus beta, that is 180 degrees. So the sum of those two angles is 180 degrees. But those two angles are defined as one-sided interior angles. So if we found out that the sum of two one-sided interior angles is equal to 180 degrees, and therefore according to rule 18, remember we have the sum of two one-sided interior angles that is equal to 90 degrees, then the two one-sided interior angles must be located between two parallel lines, and those two angles are located between line QP and line PM, line QB and line PM, and therefore according to rule 18, line QB must be parallel to line PM. So fit quickly on rule 18. According to rule 18, if the sum of two one-sided interior angles is equal to 180 degrees, then they are located between two parallel lines. Again, if the sum of two one-sided interior angles is equal to 180 degrees, then they are located between two parallel lines. So in the drawing we have line A that is parallel to line B. This is the line C that intersects with those two parallel lines A and B at those 2 points. Those are angles alpha and beta defined as one-sided interior angles. And we know it is given us that angle alpha plus beta is equal to 180 degrees. So the sum of those two one-sided interior angles is equal to 180 degrees, and therefore we can conclude from it that line A is parallel to line B. Okay, it is actually the opposite rule of rule 17. So we can implement rule 18 in our drawing. One got so I mentioned before, the sum of those two one-sided interior angles is equal to 180 degrees, and therefore according to rule 18, those two angles must be located between two parallel lines. Actually, they are located between line QB and line PM. And because of the fact that the sum of those two one-sided interior angles is equal to 180 degrees, they must be located between two parallel lines. That is to say, line QB is parallel to line PM. So So it is known according to rule 18. Line QB is parallel to line PM. I repeat again, because of the fact that the sum of those two one-sided triangles is equal to 180 degrees, according to rule 18, those two one-sided triangles must be located between two parallel lines. They are located between line QB and line PM. And according to rule 18, line QB must be parallel to line PM. Okay, line QB parallel to line PM. According to rule 18. In the next step, I'll copy again this semicircle and we'll continue to analyze this semicircle with the diameter PM. So actually, this is the semicircle with the diameter PM that are coming from the original drawing. According to rule 18, QB is parallel to PM. OM equals to OP, they are both the area of the circle, that is equals to 15. PQ equals to 10 units in itself, according to what is given in the question. We have already found out that BM also equals to 10 units in itself. And our mission is to find out the length of this line segment QB that is equal to X. Okay, so in the next step, we'll join points Q and O together by a straight line. What is the definition of line segment QO? Line segment QO starts from point O, that is the center of this semicircle, and ends at point Q, that is the point on the semicircle itself. So this is exactly the definition of a radius. Therefore, Q is the radius of this semicircle that is equal to 15 units in its length. In the next step, we join points O and B together by a straight line. OB is of course the radius of this semicircle that is equal to 15 units in its length. According to rule 18, QB is parallel to PM. Those two angles, they are defined as alternating angles. I repeat again, those two angles, they are defined as alternating angles, and they are located between the parallel lines QB and PM. Therefore, according to rule 15, those two alternating angles must be equal to each other in their sizes. So I repeat quickly on rule 15. According to rule 15, alternating angles between parallel lines are equal to each other. So in the drawing we have line A that is parallel to line B, And we have those two angles alpha and beta that are defined as alternating angles. And because of the fact that those two alternating angles alpha and beta are located between the two parallel lines A and B, they must be equal to each other in their sizes. That is to say, alpha equals to beta. So as I mentioned before, we can implement Rule 15 in our drawing because of the fact that those two alternating angles, they are located between the parallel lines QB and PM, therefore they are equal to each other. So this is angle POQ, that is equal to this angle, that is actually angle OQB. And they are equal to each other according to Rule 15, because of the fact that they are located between the parallel lines QB and PM. So if we define angle POQ as alpha, then this angle must be also equal to alpha because they are equal to each other according to Rule 15. So in the next step, I will present to you, I will repeat quickly on the law of cosines, and we will implement the law of cosines in the green triangle POQ, and also in this triangle QOB. Actually, the law of cosines is true in any triangle. So actually, this is triangle ABC. That could be any triangle. We know that this is side AB. That is equal to A units in its length. This is side AC. That is equal to B units in its length. This is side BC, that is equal to C units in its length. And this is angle theta. Angle BAC equals to theta according to our definition. So in this triangle ABC, that could be any triangle. Cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. But again, in this triangle ABC, that could be any triangle. Cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So in the next step, I'll copy this green triangle PQO, and this new pattern, we will implement the Pythagoras theorem of this green triangle POQ. PQ equals to 10 units in its length according to what is given as a question. PO equals to 15, it is actually the radius of the circle. OQ also equals to 15 units in its length, it is also the radius of the circle. And angle POQ equals to alpha. So in this triangle POQ, according to the law of cosines, we'll get that cosine alpha, this will be equation 1, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. Repeat again, according to the law of cosines, in this triangle POQ, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. In the next step, I'll copy this triangle OQB in a new page and we will implement the law of cosines in this triangle OQB. Side OQ equals to 15 units in its length. Side OB also equals to 15 units in its length. They are both the radii of the circle, this equals to 15. And QB equals to X, it is the line segment that we are looking for in this question. And finally, angle OQB is equal to alpha. So really, this is triangle OQB that I copied from the original drawing. It is not from the original drawing, but from here, from this drawing. So we'll implement the law of cosines in this triangle OQB. This will be equation 2. According to the law of cosines in triangle OQB, cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. Repeat again, according to the law of cosines in this triangle OQB, cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. So we have two equations from cosine alpha. Therefore, we create equation 3 that states that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. You see, cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. cosine alpha according to equation 1 is equal to 15 square plus 15 square minus 10 square over 2 times 15 times 15. And cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 2 is equal to x squared plus 15 square minus 15 square divided by 2 times x times 15. Repeat again. This is actually equation 3 that says that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. We focus on the denominator of those two expressions. In the denominator of those two expressions we have 2 times 15. So 2 times 15 will get cancelled. And in this equation we have, in this side of the equation we have 15 squared minus 15 squared, that is 0. So those two expressions will get cancelled. And we left here x squared over x, that is x. X squared over x is x, so in this side of the equation we left only with x. And in the other side of the equation we left with 15 squared plus 15 squared minus 10 squared divided by 15. So according to equation 3, x equals to 15 squared is 225. So 225 plus 225 is 450. Minus 10 squared, that is 100. So it is minus 100 divided by 15. So according to equation 3, we have found out that x equals to 450 minus 100 is 350 divided by 15. So here we divide both the numerator and the denominator of this number by 5, and we get that x equals to 350 over 5 is 70 divided 15 over 5 is 3. So in total we found out that line segment QB is equals to x is equal to either 70 over 3 units in its length, or in terms of numbers 70 over 3 is 23 and 30 units in its length. And that is the answer to the second question. Repeat again, we found out that the length of this line segment QB is equal to x is equal to either 70 over 3 units in its length, or the length of QB is equal to x is equal to 23 and 30 units in its length. So we finish with the second question. In the next step I will summarize the lecture. We'll start with the first question, of course. The first question Our mission is to find out the area of this circle that is inscribed by this trapezoid ABCD. So, in the drawing, we have trapezoid ABCD that blocks this circle. In addition, we know that this is line segment AM that is equal to A units in its length. This is line segment AB that is equal to B units in its length. Again, our mission is to find out the area of this circle that is described by this trapezoid ABCD. First of all, we define the center of this circle. This point is point O. We define the point of tendency of tangent AD with this circle. This point is point P. And finally, we define the point of tendency of this tangent BC with this circle. This point is point Q. So here, we actually implemented rule 2. If we focus on this common example point A, from this common example point A, we have two tangents to this circle, tangent AP and tangent AM, and according to rule 2, they are equal to each other. That is to say, AP equals to AM, but AM equals to A, therefore AP must be also equal to A units in itself, according to rule 2. Likewise, according to the same rule 2, if we focus on this common example point B, from this common example point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM equals to B units in its length, according to what is given as the question. Therefore, BQ must be also equal to B units in its length, according to rule 2. So BQ equals to B units in its length, according to rule 2. In the next step, we join points O and Q together by straight line. Point O is the center of the circle, point Q is the point of the circle itself, so this is exactly the definition of a radius. Therefore, OQ is the radius of this circle, so we define the radius of this circle as x, therefore OQ equals to x. And because of the fact that the radius OQ is drawn to point Q, that is the point of tendency of tangent BC with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and P together by straight line. OP is of course the radius of this circle that is equals to x, and because of the fact that the radius OP is drawn to point P, that is the point of tendency of tangent AD with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent AP will be perpendicular to the radius PO. If tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we did a construction. That is to say, from this point A, we draw perpendicular on BC. Again, from point A, we draw perpendicular on BC. So actually, this angle equals to 90 degrees. This angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point N. By doing this construction, we created those two angles that are defined as one-sided internal angles. Those two angles are located between side AD and side BC. And because of the fact that ABCD is a trapezoid, in trapezoid ABCD, side AD is parallel to side BC. So those two one-sided internal angles are located between the parallel lines AD and BC, and therefore they are equal to each other, and therefore the sum of those two one-sided internal angles must be equal to 180 degrees. But this angle equals to 90 degrees according to our construction. So 90 degrees plus the size of this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 17. Therefore this missing angle must be equal to 90 degrees in its size. In the next step we did another construction, that is to say from this point into O, that is the center of this circle, we do perpendicular on AN. Again from point O we do perpendicular on AN. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AN. This point is point T. By doing this construction, we created the small quadrilateral APOT. Inside this small quadrilateral APOT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this 4 facing angle must be equal to 90 degrees in its size. Likewise, inside this quadrangle, the lower quadrangle TOQN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 facing angle, in total it must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this 4 facing angle must be equal to 90 degrees in its size. So, in total, if you want that the big angle POQ equals to 90 degrees plus 90 degrees, that is 180 degrees. Repeat again. The big angle POQ equals to 180 degrees in its size, and we know that any angle that is equal to 180 degrees in its size, it is a straight line. That is to say, POQ, line segment POQ, angle POQ, that is also line segment POQ, is a straight line. Repeat again, line segment POQ is a straight line. If POQ is a straight line, then PQ must be also a straight line. So PQ is also a straight line. So inside shape APQN, inside this shape APQN, we have 1, 2, 3, 4 sides. Repeat again. In shape APQN, we have 4 sides, and therefore shape APQN is a quadrilateral. But inside quadrilateral APQN, we have 4 right angles. And we know that any quadrilateral that has 4 right angles must be this rectangle in front of a square according to rule 5. Therefore, we relate to this quadrilateral APQN as a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle APQN, side AP must be equal to the opposite side QN. But AP is A, therefore QN must be also equal to N in its length. Likewise, according to the same rule, in the same rectangle APQN, side PQ must be equal to the opposite side AN. But PQ in total equals to x plus x, that is 2x, therefore AN must be also equal to 2x units in its length. What is the length of the missing line segment BN? From the dominant it is very easy to see that BN in total equals to BQ minus NQ. Again, BN equals to BQ minus NQ. So BN equals to BQ. BQ is B minus NQ. NQ is A. So in total BN equals to B minus A units in its length. So in the next step, I copied the right triangle A and B in a new page, and we implemented the Pythagoras theorem on this right triangle A and B. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is triangle A and B that I copied from the original drawing. This triangle A and B, according to the Pythagoras theorem, AB squared, that is the square of the hypotenuse, equals to AN squared plus NB squared. So AB is A plus B, therefore AB squared is A plus B squared, and it is equals to AN squared. AN is 2x, therefore AN squared is 4x squared, plus NB squared. NB is B minus A, therefore NB squared is B minus A squared. So in total we found out that A plus B squared equals to 4x squared plus B minus A squared. We open the brackets on both sides of this equation, and we found out that A plus B squared equals to A squared plus B squared plus 2 times AB, and it is equal to 4x squared plus B minus A squared. B minus A squared equals to B squared plus A squared minus 2 times A times B. Here we have A squared on both sides of this equation, so A squared will get cancelled, and we have also B squared on both sides of this equation, so B squared also will get cancelled. After cancelling those two expressions, this side of the equation we left with 2AB, and the other side of the equation we left only with 4x squared minus 2AB. So in total we found out that 2AB equals to 4x squared minus 2AB. We added 2AB to this equation, and we found out that 2AB plus 2AB is 4AB, so 4AB equals to 4x squared. Here we divided this equation by 4, and finally found out that 4 times AB over 4 is AB, and 4x squared over 4 is x squared. So in total we found out that x squared equals to AB. Our mission is to find out the area of this circle. Actually we know that the area of any circle equals to pi times the radius of the circle squared, and therefore the area of this circle must be equal to pi times the radius of this circle squared. The radius of this circle is x, therefore the radius squared is x squared. So in total the area of this circle must be equal to pi x squared. But x squared is AB, so we substitute x squared here by AB, and find out that the area of the circle is pi AB. The area of the circle is pi AB square units. We finished the first question. Next step I presented to the second question. We solve the second question of this lecture. In the second question, our mission is to find out the length of this line segment qubit is equal to x. So in the original drawing, we have a semicircle. Inside this semicircle, we have line segment chord AB that is equal to 10 units in itself. This is called PQ that is also equal to 10 units in itself. AB, that is the diameter of this semicircle, equals to 30 units in itself. And QB is the qubit is equal to x, is the missing line segment. That is the line segment that we are looking for in this question. So our mission to find out the length of qubit is equal to x. We have to find out the value of x. So first of all, we define the center of this semicircle. This point is point O. We know that the diameter of the semicircle AB is 30. Therefore, the radius must be equal to half of it. That is to say, the radius must be equal to 30 over 2, that is 15. So OA is the radius of this circle, that is 15. OB is also the radius of this circle, that is 15. In the next step, we join points P and O together by set line. Point O is the center of the circle, point on the semicircle, point P is the point of the semicircle. Therefore, OP is the radius of this semicircle, that is 15. In the next step, we completed this semicircle to a circle, and we extended the radius PO by side line until it touches the circle at this point. So this is the touching point of the extended PO with this circle. We define this touching point as M. OM is also the radius of this circle, that is 15. In the next step, we join points M and B together by straight line. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if this angle is theta, then this angle must be also equal to theta, because they are equal to each other according to the rule that I mentioned. In the next step, I prove that this right angle APO is congruent to this right angle, triangle MOB. So why those two right angles can go into each other? First of all, side PO equals to side OM. They are both the radius of the circle, that is equal to 15, and therefore they are equal to each other. In addition, those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. And finally, side AO equals to side OB. They are both the radius of the circle, therefore they are equal to each other. So I can prove that this triangle APO can go into this triangle OBM according to side angle side rule. We have those two sides and the angle that is included between those two sides that are correspondingly equal to those two sides and the angle that is included between those two sides in triangle BOM. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we will derive that side PA equals to side BM. According to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides must be also equal, the two corresponding sides PA and BM must be also equal to each other. Read again. AP equals to BM, but AP equals to 10. According to what is given as the equation. So from this equation, 10 equals to AP equals to MB, we derive that MB also equals to 10 units in its length. This is side MB, this equals to 10 units in its length. In the next step, we know that PO, PM, this is called PM, that passes from point O, and we know that any chord that passes through the center of the circle must be the diameter of the circle or semicircle. So PM is the diameter of this semicircle, so I copy this semicircle with the diameter PM, and we analyze this semicircle with the diameter PM. So This is the semicircle with the diameter PM that I copied from the original drawing. QB equals to X units in length. This is the line segment that we are looking for in this question. PQ equals to 10 and BM also equals to 10. In the next step, we know that PQ equals to BM, so those two line segments are equal to each other. In the next step, we extended those two line segments until they intersect with each other at this point E. And because of the fact that those two line segments are equal to each other, each of these line segments is equal to 10 units in step. When you extend two line segments that are equal to each other until they touch each other, then the extended line segments must be also equal to each other. That is to say, QE must be also equal to BE. So if QE is y, then BE must be also equal to y because they must be equal to each other. So in total, side EP equals to y plus 10 and side EM also equals to y plus 10. From those two equations, we derive that EP equals to EM. So in triangle EMP, side EP equals to side EM, therefore it is an isosceles triangle. And we have the rule that in front of equal sides in the triangle there are equal angles. So in front of this side EP we have this angle, in front of this side EM we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So this angle, if the size of this angle is better, then the size of this angle must be also equal to each other because they are equal to each other according to the rule that I mentioned. In the next step, we have completed this semicircle to a circle. So here we have quadrilateral PQBM that is inscribed by this circle, and we have the rule that says that any quadrilateral that is inscribed by a circle, then its two opposite angles must be equal to 180 degrees. So this quadrilateral PQBM is inscribed by a circle, and therefore those two opposite angles that inside quadrilateral PQBM must be equal to 180 degrees in their size. But this angle equals to beta, so angle beta plus this missing angle in total must be equal to 180 degrees. Therefore this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of two opposite angles in quadrilateral PQBM that is described by a circle. Likewise, the sum of those two opposite angles must be equal to 180 degrees. But this is angle beta. So this missing angle must be equal to 180 degrees minus beta. Because 180 degrees minus beta plus beta is 180 degrees. This is the sum of those two opposite angles in quadrilateral PQBM that is described by a circle. So this angle must be also equal to 180 degrees minus beta. In total, we have found out that this is angle beta, and this angle is 180 degrees minus beta. The size of this angle is 180 degrees minus beta. So those two angles are defined as one-sided interangles. The sum of those two angles is 180 degrees. Why? Because 180 degrees minus beta plus beta is 180 degrees. So the sum of those two angles, the sum of those two one-sided angles is equal to 180 degrees. And according to rule 18, if the sum of two one-sided angles is equal to 180 degrees, then they are located between parallel lines. Those two one-sided angles, the sum of those two angles is 180 degrees, are located between line segment QB and line segment BM. And according to rule 18, they must be located between two parallel lines. Therefore, QB must be parallel to PM according to rule 18. Again, QB must be parallel to PM. Here we have QB must be parallel to PM according to rule 18. So in the next step, I copied again this semicircle, this semicircle with the diameter PM, and we continue to analyze this semicircle with the diameter PM. So we're showing this is the semicircle with the diameter Pn. Point O is the center of the circle. OP is the radius of the circle, that is 15. OM is also the radius of the circle, that is 15. OQ is the radius of the circle, and OB is also the radius of the circle. PQ equals to 10, and BM also equals to 10. We have already found out that according to rule 18, side QB is parallel to the opposite side PM. Side QB equals to side QB is parallel to side PM. QB is parallel to PM. So those two angles are defined as alternating angles, and they are located between the two parallels QB and PM, and therefore they are equal to each other in their sizes. Again, angle POQ is equal to angle OQB according to rule 15. So if we define this angle as alpha, then this angle must be also equal to alpha, because they are equal to each other according to rule 15. According to rule 15, alternating angles between parallels are equal to each other. Those two alternating angles that are located between the parallels QB and PM must be equal to each other in their sizes. So if this angle is alpha, then this angle must be also equal to alpha according to rule 15. In the next step, I presented to you the law of cosines, and we implemented the law of cosines in this grand triangle PQO, and also in this triangle QOB. So what is the law of cosines? The law of cosines is through an n triangle. According to the law of cosines, this is triangle ABC, this could be any triangle. The length of side AB is A units, the length of side AC is B units. Side BC equals to C units in its length. This is angle theta. So in this triangle ABC, that could be any triangle. Cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So in the next step, I copied this green triangle here and implemented the law of cosines in this green triangle, triangle QPO. According to the law of cosines in this triangle QPO, cosine alpha equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. Repeat again. According to the law of cosines in this triangle QPO, cosine alpha equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. Likewise, I copied this right triangle OQB in this here, and we implemented the law of cosines in this triangle OQB. This is angle alpha. So this is triangle OQB that I copied from the original drawing. This triangle OQB, according to the law of cosines, cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. Again, according to the law of cosines in this triangle OQB, cosine alpha equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. So we have two different equations for the value of cosine alpha. This is equation 1 and this is equation 2. Therefore, in the next step, we created equation 3 that states that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. So cosine alpha according to equation 1 equals to 15 squared plus 15 squared minus 10 squared over 2 times 15 times 15. And it must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 2 equals to x squared plus 15 squared minus 15 squared over 2 times x times 15. So this equation means that cosine alpha according to equation 1 equals to cosine alpha according to equation 2. So if we focus on the denominator of those two expressions, we have 2 times 15 on both of the denominators, so 2 times 15 will get cancelled. Here we have 15 squared minus 15 squared is 0, so those two expressions also will get cancelled. So in this side of the equation we left only with x squared over x, that is x. In the other side of the equation we left with 15 squared plus 15 squared minus 10 squared over 15. So in total, according to equation 3, we found out that x equals to 15 squared plus 15 squared minus 10 squared over 15. So So x equals to 15 squared is 225, so 225 plus 225 is 450, minus 10 squared. 10 squared is minus 10 squared is 100, so it is minus 100 divided by 15. So x equals to 450 minus 100 is 350 over 15. So in total, according to equation 3, we can find out that x equals to 350 over 15. We divided both the numerator and the denominator of this number by 5. So 350 over 5 is 70, and 15 over 5 is 3. So in total, we should find out that the length of this line segment QB, is equal to x. It is equal to either 70 over 3 units in its length, or QB is equal to x is equal to 23 and 3 units in its length. Okay, thank you very much.